Sounds like it's working. Hopefully everyone can hear me. Welcome. Despite the rumors of snow, we're all still here. Just to let everyone know, this lecture is being recorded for later viewing. It's not available live, but we'll have it aligned with the others. And of course, this is part of the Eugene P. Wigner Distinguished Lecture Series in Science, Technology, and Policy that we launched on the 4th of November in 2013 on the occasion of the 70th anniversary of first criticality of the graphite reactor. And the series is organized by our corporate fellows with the goal of invigorating scientific discovery, spurring technological innovation, and initiating productive science policy debate. Of course, we're honoring Eugene Wigner, chemical engineer by training, physicist by inclination, and also by recognition in the form of the Nobel Prize in Physics in 1963 for his work on atomic theory and the role of symmetry. He was also a founder of the field of nuclear engineering and really acts as a bit of a role model for our interest in coupling fundamental understanding with end-use applications that will have an impact in the broader world. And of course, he was research director of the then Clinton labs in the mid-40s, immediately after the end of the Second World War, and we can trace many of ORNL's key strengths today to his vision for transforming what was really, at the time, just a pilot-scale plutonium production facility, and the semi-works as it was called, into what has become a major research lab. Our lecturer today is Roald Hoffmann, who received the Nobel Prize in Chemistry in 1981 for his work to extend our understanding of chemical reactions. He's also a playwright, a poet, and an ardent proponent of communicating the value of science to the public. He's currently the Frank H.T. Rhodes Professor of Humane Letters Emeritus and a Professor of Chemistry Emeritus in the Department of Chemistry and Chemical Biology at Cornell University. He joined the Cornell faculty in 1965 after receiving a BA in chemistry from Columbia and a PhD in chemical physics from Harvard. He's gained global recognition for his creative application of theory to organic and inorganic chemistry. He's explored the electronic structure of stable and unstable molecules across the periodic table and of transition states and reactions. He applies a variety of quantum chemical computational methods, as well as qualitative arguments, to problems of structure and reactivity of both organic and inorganic molecules of medium size into extended systems in 1, 2, and 3 dimensions. No surprise, he's published hundreds of refereed journal articles, 5 volumes of poetry, 3 plays, and several books on the relationship of science, art, and philosophy. In this context, it's interesting to note that English is his 6th language. I'm not sure what language today's lecture will be in, but there's no simultaneous translation, so you'll just have to wing it. He's hosted a public television series on chemistry and helped to organize a series of weekly cabarets entertaining science in New York's Greenwich Village. And he's received numerous honors in addition to the Nobel Prize, the National Medal of Science in 1983, more than 25 honorary doctorates, awards from the American Chemical Society in 3 different subfields, the A.C. Cope Award in Organic Chemistry, the Award in Inorganic Chemistry, and the Pimentel Award in Chemical Education. I think simultaneously winning the awards in Organic Chemistry and Inorganic Chemistry probably violates some kind of fundamental principle. It's sort of like interspecies breeding or something. He's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. He's a foreign member of the Royal Society, the Indian National Science Academy, the Royal Swedish Academy of Sciences, the Finnish Society of Sciences and Letters, the Russian Academy of Sciences. You can tell, coming from Cornell, he has affinity for very cold places. The North Rhine-Westphalia Academy of Sciences, Humanities, and the Arts, and the Leopoldina German National Academy of Sciences. In his lecture today, Dr. Hoffmann will discuss the chemical imagination at work in very tight places. Please join me in welcoming.
Thank you. Let's see, can we switch? Yes. So, about Eugene Wigner, he began as a chemist. With chemical engineering, he followed his parents' desires, but he got his PhD with Michael Polanyi in the Kaiser Wilhelm Institute. And the PhD thesis was on the formation and decomposition of molecules, which was Polanyi's interest at that time. But then he found chemistry too difficult for him. And so he went on to the Gruppenpest, to the group theory that and the study of symmetry. So So if I were in Europe, I wouldn't have to say anything. But here it's coming. So this is Obelisk applying high pressure to some poor Romans. It's done in more controlled fashion, and I want to talk to you today about this topic with this funny title, which I will. Every word in it has some meaning, and I'll make that clear in time. This is work largely together with a very good solid-state physicist, Neil Ashcroft. Quite spontaneously, 40 years we were together at the same university, but only after about 40 years did we form a joint research group, and our interests drew us together, and it was a postdoc who had the courage to go over to talk to Neil that it was the impetus for that. And the work has been supported by the National Science Foundation, and also part of the work that also has a connection to Oak Ridge is the E-Free project that is mainly to the Carnegie Institution of Washington. And some of you know the people involved there. So the units here that we'll be talking about are gigapascals, in which I'll be speaking, approximately 10,000 atmospheres, and the other calibration is that the pressure at the center of the Earth is about 3.5 million atmospheres, about 350 gigapascals. The pressure in the larger planets is proportionally greater, so this is the reason for the geochemical, astrophysical interest in the high pressure. The other sort of calibration is in terms of what does the things. As I'll say a few times, the only imperative under high pressure is to get closer together for the density to increase. And so the volume decreases. The amount of matter may be the same, but it's interesting to see by how much the volume decreases. It depends on what it is. If it's hydrogen going from the solid to the pressures at the center of the Earth or a major planet, there is a volume decrease of a factor of 10. If it's a hard metal or iron or gold is not particularly hard, then the decrease is much smaller. For molecules, molecular crystals, it is less. Even for metals, it varies from lithium for about a factor of 5 to a factor of 1.7. So along a linear dimension, it's the cube root of that. So you can see what happens to the distances between atoms as you go to these very high pressures. This is a world of Superman squeezing things or diamond anvil presses. Chemists are used to high pressure, but it's a little different world. Here is the world's most successful industrial process, the Haber-Bosch process for making ammonia from nitrogen and hydrogen. How successful it is comes from me being able to tell you, based on some measurements by others, that half the nitrogen atoms in your bodies have seen the inside of a Haber-Bosch factory. Or half the people in this world would not be alive if it were not for the synthetic fertilizers that are made in this way. Right, you can go out and buy a vessel to build a new Haber-Bosch factory of substantial volume that operates at 150 to 300 atmospheres. That's a typical process the chemical industry can handle routinely. And for the people who are studying things here in diamond anvil presses, such pressures are known as near vacuum. So there is a difference on perspective in this. We are going to be talking about millions of atmospheres compared to 150 to 300. It's not your bicycle pump. Okay, so how is this studied? For some decades now, the way to study it is with 2 diamonds, so it's expensive. It's an expensive process, and the most ominous sound in a high-pressure laboratory, very well known to people in the field, but even I have heard it as a theoretician, is the sound of diamonds cracking. And that happens a lot of the time, so it's fairly expensive research. The actual diamond, there's a gasket, a hole drilled in a piece of metal, diamonds above and below, and pressure through then a combination of mechanical hydrostatic pressure. You can get up to those pressures that I'm talking about, of millions of atmospheres. But here is what you have, and that is a press that uses also diamonds in another form, but a larger reaction chamber. The reaction chamber, this is macroscopic chemistry, but of course, for the highest pressures, it's a tiny volume because pressure is force per unit area, and the area goes down of the diamonds that are compressed, doing the compressing. But in these larger presses, it's a few millimeters cubed, so you can make some milligrams of the material. And these are some of the diamond threads, one suggested structure, diamond-like threads and nanothreads that have been made in the cell that is here, that was constructed by a Paris-Edinburgh collaboration. Down here is, well, you recognize it's an old Mercury capsule re-entering, but it's what I found as an image of a shock wave in front. So this is the other way of studying high pressure. There are still also intermediate ways, and that is in shock tubes. And to nobody's surprise, the people who are good at making atomic bombs are also good at shock tube research, because an explosion is involved. And so the Russians and the Americans are very good at this. The conditions in a shock wave are conditions which are where they're not static conditions where you can impose a temperature and a pressure for some length of time. They are conditions in which some very short period of time, of the order of nanoseconds, or a little bit longer, the pressure and the temperature rise together. So it's not a static condition, but yet you can do measurements under those, and very good measurements under those. The oldest story, and still illustrative, is in the high-pressure field, is the story of diamond and graphite. So here are the densities of these 2 allotropes of carbon, which are within 40th of an eV of each other in free energy under normal conditions. But as you see, the densities are immensely different. And what this means is, since under pressure, it's the density that matters, and the density at a given pressure is already a hint of what's going to happen when you apply pressure to this. So that applying just a little bit of pressure on the scale of 100 gigapascals will convert graphite to diamond. Now, how big a barrier it has is an interesting story. The barrier in this case is not gigantic, but that is in fact how diamonds are made. in the mantle and then brought up by kimberlite pipes. Now, you can duplicate this in a laboratory, but what you get is not gem quality diamonds, but industrial grade diamonds of poorer quality. Maybe General Electric, who has done this process for some time, maybe they could make gem quality diamonds. Maybe they had a deal with De Beers Mines not to make gem quality diamonds. If you tomorrow come up with a catalytic process for making gem quality diamonds, I would strongly suggest that you not publish it, because Agent 0010 will be immediately set out by the Russians to do away with you. It is not in the interests of Russia or a number of other countries and that great conglomerate of De Beers Mines that gem quality diamonds be cheap. It's a multi-billion-dollar business that they stay expensive. And so we don't know really the story. There are also diamonds makeable by other methods. What happens under pressure, given the imperative to get closer together for the density to increase, is any gas turns into a liquid, turns into a solid. This is trivial stuff. What's much more interesting in some way is if the initial material had a band gap or a gap between filled and unfilled orbitals, if you're thinking of a molecule, those filled orbitals spread out into a band. What determines the bandwidth is, in chemical language, the overlap between the wave functions of the orbitals and the atoms. Physical language, a transfer integral. It's the same thing. It's the overlap between the atomic functions. They get closer, the overlap gets bigger. The bands spread out, the filled bands and the unfilled bands, and eventually there is perhaps a crossover. Things may be complicated by symmetry, but this is what happens, and anything is expected to turn metallic under high pressure. And actually, the interesting thing in the last decade has been that some materials that are metallic to begin with, under pressure, turn insulating, actually, semiconducting, but eventually they return to metallicity too. So everything turns metallic. And to a chemist, this is a little hard to take. I mean, xenon is the proverbial lead balloon. You have a balloon of xenon that sinks instead of a helium. The density rising, the density is higher of xenon, and that you can make xenon liquid, some of us have seen that. It's not hard. You can make it solid very easily. But that a noble gas turn into a metal, that takes a little thing for your mind to wrap in. But that has been observed, but not argon or neon or helium, but yet helium surely is liquid inside some of the more dense planets. Ionic substances, no one has yet metallized sodium chloride, but moderately ionic substances and polarizable ones such as cesium iodide and barium telluride have been made metallic. To a chemist, perhaps the most striking demonstration of how different this world is are two substances that we're used to, CO2 and N2. CO2, of course, we're used to dry ice, all of us. And we don't think too much about why it is that silicon dioxide is not a gas, but CO2 is. But CO2 under pressure turns into an equivalent, into a structure which is like one of the quartz structures, and eventually can even turn into a high-pressure structure which is like that of Stishovite high-pressure quartz. Nitrogen, the world's one of the two world's most stable diatomics with respect to atomization, with a nice triple bond in a short distance, at elevated pressure and temperature turns into a three-coordinate structure like that of its congeners underneath, not exactly like, but similar to the structures of arsenic and antimony, and one of the structures of phosphorus, a three-coordinate net. So the effects of the pressure are gigantic. Hydrogen has been a holy grail here. Especially Neil Ashcroft has contributed a lot to the theory of hydrogen. Hydrogen surely goes metallic at pressures of 500 GPa or above. This is a typical graph which shows how experiment and theory go with time. I haven't brought it up to date, but you know what these graphs are like. The moment that the experimentalists reach a pressure which the theoreticians predict that something will happen, the theoreticians change that pressure. That's what this graph says. Arametz and Troyan have metallized hydrogen. So hydrogen has been metallized in shockwave conditions by Nellis and co-workers. There's no doubt about it. That's hot fluid hydrogen at elevated temperatures is metallic, as measured by the reflectivity. No one has time to do a conductivity measurement under shock tube conditions, but you can study the reflection of light from it. This has been questioned. There is a particularly nasty polemical article by 3 experts in the field that is fun to read about these experiments. These experiments are difficult to duplicate, but I think they're probably right. This is now under static diamond anvil conditions, but very special preparation. Hydrogen has been made metallic. Neil has suggested it's a superfluid, and that is interesting. That also the attraction is that it'll be a very likely a superconductor. Neil had an idea that somehow you could induce hydrogen to metallize easier if you distracted the hydrogen atoms. Hydrogen goes to hydrogen molecules. They're there in a solid. The hydrogen molecules get closer together, and eventually that's expected to go metallic. He thought maybe you could get it to go metallic at a lower pressure if you bonded the hydrogen to something else, like raisins throwing in, distracting the hydrogen. Some problems with it, but it led to his thinking about hydrogen-rich materials, and some of these have been studied. You can have transition metal ions which have actually as many as 9 hydrogens bonded to one transition metal. And we have the structures of these, thanks to neutrons, available. I don't think the structure was done here, but we have the structure of these various salts. Neil thought that perhaps this could be done with something like silicon, and that was actually our entry into the field. Does it bother anyone that silicon is silicon tetrahydride, the silicon analog of methane, is particularly nasty? Yes and no. It's a problem, but it's made in ton qualities for etching in the semiconductor industry, and that these things can be controlled. It helps in a high pressure group if you have a fearless person who likes to do chemistry. And so, because some of the materials that one thinks up are not particularly nice. So this was the beginning of our first study, and Wojciech Ruchala was the postdoc who went over to Neil on silane, and we learned a tremendous amount from that first study on silane. So here's the problem. Silane, it exists. As I told you, it's made in ton qualities. Its crystal structure is not known, not very well known. The reason is that like methane, like Buckminster fullerene, it's almost a sphere. So that it's a rotational solid. It rotates around, and that makes the structure, it doesn't settle down. So we were faced with guessing a structure for the material under very high pressure. So when we asked Neil, what do you think SiH4, what is its structure? He came up with this. Now, you have to get used to, but most of you are. This is not, the gold is silicon, the green is hydrogen. This is not silicon 9H8, this is silicon H4. Each of those 8 atoms at the corners of the unit cell is shared with 8 unit cells, 1 in the middle, so that's 2 silicons in a unit cell, and 8 hydrogens, which make silicon 2H8, which is silicon H4. Okay, we're going to see these again. He suggested this, and this makes zero chemical sense, but it's totally consistent. So physicists, so Cornell has the world's best agriculture school. So the people in the agriculture school go over to our physics department and say, could you model a cow for us? And what they say was, let's begin with a sphere, and then we'll put the cowness as a perturbation. Okay, so this is, my daughter is a physicist, but I will have assorted things to say about physics here along the way, which is, it's a weakness of the human mind, simplicity, to believe that the world is as simple as our minds. Just listen to the political candidates in New Hampshire. Right? If we shoot down all the planes between the United States and Mexico, we'll solve the drug problem and that kind of stuff. So the thing is that scientists are no better than other people. Why should they be? And so they also fall for simplicity. That's what's at work here, symmetry and simplicity. The world is as it is. So what could one suggest? So there is a use for the periodic table. Silicon's under carbon, and any compound that you could imagine for carbon, you could imagine for silicon. Doesn't mean it'll have the same stability. This periodic table is a matter of being the same and not the same, and it's very interesting in that. But here are 3 structures with tetrahedral silane, SiH4 in a crystal. And no, that's not an SiH. That if I repeat the 8 unit cells around it, it'll generate as much a tetrahedron as that one is. It's just a piece of another silane. So these are structures with 2, 1, and 4 molecules per unit cell, as it happens, that are possible suggestions from knowing the chemistry of silane. But now there is a little more which chemistry can bring to this, because here are 3 structures in which the silicon is 6-coordinate. Now, I know that from inorganic chemistry, one of the differences between silicon and carbon above it is carbon hates 5 and 6 coordination, but silicon is perfectly happy with it. So this is a structure, for instance, not of silicon. This is the actual structure of tin tetrafluoride. So you go down further in the periodic table, and fluorine, and no, that's not a silicon H6. That's 2 hydrogens are in a unit cell. The 4 hydrogens on the faces of the unit cell are shared with 2 unit cells. So that's silicon 2 plus 4 over 2, which makes silicon H4. But it's octahedral silicon. Here's a rutile type structure for those of you. Here's another one. These are based on knowing something about silicon chemistry. Here are 7 of the 13 structures we tried. And I won't tell you what came out. But maybe this structure is not as bad as it seems, because the chemist's intuition, as good as it is based on P = 1 atmosphere chemistry. And the rules are off in some ways, as you saw, as you go to higher pressures. here is the article we wrote on basis of what we learned. A few things about this in a chemical journal. Oh, we managed to sneak in here something. We have a chart about what happens, different characteristics, different pressures. So here we put in about the polar. The thing is, we're very bad at economics. At that time, Poland was not doing too well. Today, Poland is doing economically fantastically well, the best of the Eastern European countries. So this is totally outdated. This is an interesting story. So in Europe, you could do this. So the pressure under a stiletto heel is 100th of a gigapascal. But in the United States, you can get into trouble for doing this. So what we did was we borrowed from a Polish postdoc I had the only pair of stiletto heels that she owned for her friend's wedding. And we painted my toenails red, and that's my foot in there. And for $100, I'll sell you the original picture. So no sexism, that's my foot. What I want to tell you is a little bit about what happens to matter under high pressure that we learned. We learned a lot from the silane. We've learned subsequently. What I'm going to give you is a hierarchy of responses in structure of molecules and matter to increasing pressure, increasing density. This is not a set of rules which say this is what's going to happen. It's a set of overlapping things that happens. The first thing is penetrating the repulsive region of intermolecular potentials. Let me explain that. So intermolecular potentials, here's a crystal of benzene. And that was what was subjected in the Paris-Edinburgh pressure to 220 gigapascals and then done slowly going up and down, and which led to these remarkable nanothreads. This is what the crystal benzene looks like. What is it that holds it together? It's weak London dispersion forces, van der Waals forces, maybe multiple interactions. The first multiple is a quadrupole in here, not much to go on. There's no dipoles in this material. These potentials have been known for some time, modeled. They depend on a number of electrons. They are very small for helium, a few wave numbers or less, and they are larger for other things. The greater the dispersion forces, the higher the melting point of the solid, the boiling point of the liquid. They are modeled by 1 over to the R6 for very good theoretical reasons, attractive part, and are modeled by 1 over R to the 12th repulsive part. Everyone cares about the attractive part because that's behind making sense of phase transitions. As a first approximation, nobody cares about the repulsive part of the van der Waals potential. Some people care so little, they replace it by a wall going up to infinity. Well, under high pressure, there ain't no walls. Everything collapses when you apply pressure. It turns out that this is very deceptive, and it's possible to push a way into the van der Waals repulsive part of the potential, of the van der Waals potential, without much cost. Let me show you a little bit. Now you have to believe the theory. Here is for silane, and here is for H2 under pressure. These are under solid structures. This is one of the structures, the two molecules in a unit cell under high pressure. And what I'm plotting here as a function of pressure is the distance from a green ball in one molecule to its green ball in the next molecule, the nearest neighbor contact. And what you see is it starts out at 3.1 angstroms, and here it falls in the first 10 gigapascals by 1 angstrom. What I don't show you is that the silicon-hydrogen distance changes by 3/100ths of 3,000ths of an angstrom in the same. So there is a ratio of 100 or more between how much the distance in the molecule changes to the van der Waals dispersion force, and then it gets slowly. Here is H2, and this is one structure of H2, and that's not a hydrogen atom, that's an H2 molecule, and done. But here is again this second shortest HH distance in this. The shortest is the 0.74 angstroms for the H2 molecule. And the second one, it starts out at 3 angstroms. And again, in the first 10 gigapascals, that distance goes down by an angstrom, then it goes down more slowly. So this is behind this colloquial statement. The first thing that happens when you compress any molecule is van der Waals space is squeezed out. Things get closer together, and it doesn't cost that much to go into the repulsive region of van der Waals potential. The next thing that happens is you increase coordination at main group and transition metal elements. And let me talk about this. So some of it is behind the coordination alchemy that you saw in CO2 and N2. So N2 in the gas phase or in the solid of N2 at 1 atmosphere has 1 nitrogen from the other one, 1.1 angstroms apart. The distance to the next nitrogen molecule is 2.5 to 3 angstroms. What's the coordination number of a nitrogen atom in a nitrogen molecule solid? You have to define a coordination sphere. People who are used, as many of you are, to liquids and radio distribution functions will know the problem of defining a first coordination sphere. But I would say colloquially that a nitrogen molecule in a gas is 1 coordinate, has 1 nearest neighbor. That's nice at 1 atmosphere. But it's not what's going to happen when you compress the things. They're getting closer together. So the reason it goes into this structure is it's 3 coordinate. It's still got good chemical bonding, 3 single bonds and a lone pair of electrons, but it's now got more nearest neighbors, and that overcomes 10 eV of the triple bond to go to a single bond over there. CO2 and quartz, CO2 has the carbon 2 coordinate. In the CO2 molecule, the oxygen is 1 coordinate. In quartz structure, the carbon goes 4 coordinate, the oxygen goes 2 coordinate. So this is what happens. So what's at work here? What's at work here is the same thing as the New York City subway. And that is, so now this is pressure, but now the density is increasing in the subway as you go toward rush hour. But the volume is being constant and the number of atoms is changing. That's different from compressing something where the volume is going down and the number of atoms is constant. But it's the same thing. People have done studies of the distribution of passengers in lightly frequented trains. It's actually a bimodal distribution. That is, this is psychology at work. That is, people sit as far apart from each other as they can for security or privacy reasons, unless they are lovers. Then they sit right next to each other. So there's a bimodal distribution in those studies. When you add on in this configuration, you go toward coordination number 2, and here's coordination number 6 being approached in the subway as you increase the pressure in here. You think that's bad? I want to show you. This is the Tokyo subway, and there are people hired to increase the pressure. in the Tokyo subway. This is the sardine can principle. It's nothing sophisticated. When you increase the pressure, you're going to have more neighbors. Now, let me give you an example. It forms an interesting problem for chemists. Remember that silane, and here is a structure of silane under high pressure. And there was a suggestion we had. What you form is 8-coordinate silicon. At 1 atmosphere, the silicon is 4-coordinate. This is the 8-coordinate. We suggested this structure. Pickard and Needs suggested another structure, which is also 8-coordinate. But what you see is different here is each silicon shares 2 hydrogens with 4 neighboring silicons. It's still 8/2. But it's a different arrangement, and that's slightly lower energy enthalpy than ours. So now we have silicon as 8-coordinate. But the silicon, like carbon and methane, has only 4 valence electrons. How is it going to form 8 connections? They are not normal electron pair bonds. They're something else. So let's see. What's the problem? The problem is for theoreticians to come up with a way of dealing with this. The molecule has no problems at all. The molecule is an analog computer that solves Schrödinger's equation exactly, which is why we better pay attention to it. The increased density leads to higher coordination, which leads to more bonds, full or partial. Number of electrons isn't changing, and so one needs multi-center bonding, electron-rich or electron-poor. I have worked on those for my PhD thesis on a beautiful molecule of B12H12 2-, in which a boron with 3 valence electrons is able to form 6 bonds. Very interesting bonding pattern. There are also electron-rich interactions where you can form more bonds. Silicon can go 5-coordinate. There are extended structures of lithium antimonide in which the antimony goes 2-coordinate in various ways. I want to show you one way in which you can use 1 atmosphere information. This will take me a minute to go through to get information about what will happen to high pressure. So the reason one can do this is there's something called the Cambridge Structural Database. So let me set that into perspective. Chemists, in 200 years of frenetic activity, have added 70 million compounds, well characterized, to a varying extent, what well means, to what is there in nature. Of those 70 million compounds, they're coming in at a rate of about 500,000 a year now. Of those 70 million compounds, 700,000 have had their single crystal structure done. Thanks to good planning on the part of journal editors and others, there is a depository for all those structures. About 700,000 organic structures and about 150,000 very inorganic ones. So that's the Cambridge Structural Database. At the point where you have 700,000 structures, you don't care whether some of them are good or bad. Some of them are going to be lousy. Okay, but it doesn't matter. The large numbers, the structures will tell you themselves which are the bad ones in a way, once you have such large numbers. So here is a bunch of structures in which there is F antimony F. Don't ask me why we picked antimony here. There was a reason. And what we have plotted for such structures which have a linear fluorine, antimony, fluorine, we have plotted, and the distances fluorine to antimony are R1 and R2. We've plotted not R1 versus R2, but we've plotted the length of the molecule, fluorine to fluorine, R1 plus R2, the length of the molecule, versus the asymmetry, R1 minus R2. Okay? Now, what does this have to do with pressure? Well, the length of the molecule is the dimension of the molecule. Under pressure, it's going to go down. So the length of that unit is a surrogate for the radius which goes into the volume that the molecule will occupy. And so this is long, and this is short, this is low pressure, this is high pressure. In my way of thinking, what is the pressure that's being applied? This is all at 1 atmosphere. That pressure is being applied by the other molecules in the structure, by the ions, by the chemistry of the structure that's around. And what I'm going to say that's a big assumption is that chemical pressure in the environment is maybe like the real pressure that I can apply. So what I get here, as you see clearly, this coordinate 0 means that there are two symmetrical bonds. R1 is equal to R2. So when the thing is short, R1 is equal to R2. Or, let me translate that into English. When the thing is long, the antimony is one coordinate. It's closer to one fluorine than to the other one. When the distance end to end is short, then the fluorine is two coordinates. So it's going to a higher coordination. This is how I'm using that information. Very chemical here. Then we enter a different regime. And here you might think chemistry has nothing to say. First you decrease the length of covalent bonds. You finally squeeze the molecules so close together that the pressure begins communicated through the repulsive region of the van der Waals potential, begins to tell on the bond lengths in the molecule itself. The SiH distances in SiH4 begin to change. That's this 3. And then finally you get electrons off the atoms. You get a new world, and there it looks like chemistry is not much use. I want to tell you a little bit about this world and maybe some role for chemistry. And this is something which has not reached the textbooks, which are always behind. And that is that something interesting has happened for the structures of the elements. These are not compounds, just the elements of the alkali metals and alkaline earths in the last 10 years. And the thing that has happened is that under pressure, the structures of these elements. So what do we teach undergraduate? There is a compact between teacher and student to teach only what is simple in this world. And so we teach them about FCC, HCP, and BCC structures. And we don't tell them about some of the other structures. And so the feeling is that you go to high coordination as you apply pressure. So if something starts out BCC, which is formally 8 coordinate, though it's actually 8 plus 6, everyone is happy when you compress a BCC material that it goes to FCC, because that's 12 coordinate, closest packing. But for every one of these, at some pressure, they go out of FCC and into a lower symmetry structure. And that is what's new. Here's an example. At 1 atmosphere, barium is BCC. Everyone's happy it goes to FCC at 5.5 gigapascals. Next, what happens is an incommensurate, it goes in an incommensurate structure, and then at 25 GPa, it goes into a structure. This is barium. This is not a compound. This is just barium. It goes into a structure with 288 atoms in a unit cell. Why should it do that? That's a violation of simplicity. Okay. Here is rubidium at 17.2 GPa. It goes, rubidium, into a structure where there is a kind of clathrate or zeolite structure where there are needles. This is a top view and a side view. Needles of one rubidium threading through another structure, slightly different distances. And just to make life complicated, the blue thread is an incommensurate repeat unit with respect to the green thread. And you can actually measure the melting of one relative to the other. This is actually connected and was set off in substantial part by a theoretical prediction from the Ashcroft group, by Neaton and Ashcroft, of lithium. This was a risky prediction. What is a risky prediction? A risky prediction is one where if you took an election, a vote, by experts in the field, that 99% of them would vote for the wrong thing. That's a risky prediction. Risky predictions are what makes people believe in theories. And Neil Ashcroft predicted that elemental lithium goes out of FCC into pairs, and the valence electrons go in between the lithium atoms. The actual structure done by the Edinburgh group was actually not the structure that they predicted, but it still had the important feature that it had pairing, that it had a lower symmetry. So the prediction was wrong in detail, but right in principle. And that was very important. Further complication, and this is some work on sodium, which was done by two groups, where sodium, metallic sodium, all of us have had the experience of seeing metallic sodium, if not throwing it into a urinal. I went to a high school, Stuyvesant High School in New York City, where the graduating class was 900 boys. So that's where we saw this kind of thing, behavior. It's metallic, and under pressure, it actually goes semiconducting. Here is the reflectivity falling off, and you can actually see opaquely through the sodium at a certain pressure, and then it goes metallic again. Very interesting. The electrons go off the atoms in that structure. There are sodium ions, and there is another story of electrides here, which I don't have time to tell you, but we've published on. So what is happening here? Why are things going out of close packing under pressure? So first of all, as to close packing, this is a 12-coordinate structure, whether it's HCP or cubic closest packing. That packing for ideal spheres maximizes at 74%. This was not proven mathematically till about 20 years ago, but greengrocers in the Mediterranean knew this 5,000 years ago. When they piled their oranges to be sold, they were piled in a close packing arrangement. So what's at work here? Why is this going out of this? Well, there's still 26% of space left. And I don't have to tell you that if you have little spheres, they're going to fit into the holes between those. And actually, here was an experiment done in 1727 by Stephen Hales, the first agricultural chemist, perhaps. This is a wonderful book. We're not allowed titles like this. Vegetable Statics, or an account of statical experiments on the sap in vegetables, being an essay toward a natural history, and so on. I've preserved his orthography, and he writes, I compressed several parcels of peas in the same pot with a force equal to this number of pounds, doing experiments, in which experiments, though the peas dilated, yet they did not raise the lever, because what they increased in bulk, he means volume, maybe, was by the great incumbent weight pressed into the interstices of the peas, which they adequately filled up, being thereby formed into pretty regular dodecahedrons. So peas are not stupid. They don't remain spheres. That's the fault of the assumption. It's our mind that these atoms are spheres. You compress the peas, and they don't keep sharp. Atoms don't keep sharp points. Sharp points are points of discharge. They round off the edges, but they press into it. So that's one thing. They distort to fill up all of space under pressure. Here's another thing. This is also about space and pressure. Paul Chaikin at NYU does the kind of experiments that undergraduates love to do. That is, what's the optimum packing of M&Ms? Okay? Then you can eat the results of your experiment afterwards. Turns out that M&Ms pack. Paul is interested in chaotic packing, random packing, but you know what happens if you take quarters in 2 dimensions, they pack like spheres, but in a 3rd dimension, they pack 100%. Stack quarters on top of each other. So M&Ms are halfway between quarters and spheres. So that's they have spheroids of revolution. There can be they actually pack a little better. What is happening here? Another thing, aside from changing of the atoms, is we know qualitatively, and I'll show you some quantitative, we know that spheres of unequal size can pack more efficiently than spheres of equal size. You could see that in the close packing if you had the little spheres to put into there. Okay, but now the problem of spheres of unequal size packing is an unsolved mathematical problem. There's a beautiful paper in Phys.Rev Letters 5 years ago from Frank Stilliger and Torquato, which shows a phase diagram for packing spheres of Hart sphere packing of spheres of unequal radius as a function of the radius of a ratio. It's not a completely solved problem, but lots of phases. And here are the optimum packings, and 0.74 is the sphere packing. So there are many packings of spheres of unequal size that are more dense than the spheres of equal size. And so what may be happening here is maybe an electron or a fraction of an electron jumps from one rubidium sublattice to another one, making some of it rubidium minus, I'm exaggerating, some of it rubidium plus. Those have different radii, and they'll pack better. A rather simple way, but it's not really a whole electron that could pack some more. And now we come almost to the end, but this is some of the story that I've told you about. But I want to now justify the word chemical in this story. I am a proponent of chemistry, but what I wanted to show you is I've done it along the way, but I wanted to show you here just to justify the chemistry. What was chemical in what I said? I would say that we can fight about penetrating the repulsive region of the van der Waals potential. Is that chemistry or is that physics? But as for thinking that a possible structure for SiH4 under pressure is 6-coordinate, I think that's chemistry. Because that's part of the education, only, unfortunately, my daughter, who I said has a PhD in condensed matter theory, did not have to take a chemistry course as a part of her physics major at Cornell. In fact, both of my children, between them, took one semester of chemistry, but my son is a journalist. But this is part of a chemical education. Not necessarily everything is so compartmentalized. It's only a small fraction of organic chemists who will know that silicon easily goes 6-coordinate. What's involved in the bonding in this molecule, I didn't mention it, that's the alternative structure for SiH8 under pressure. What I see when I look at those two bridging hydrogens, I see diborane, B2H6. And I know the bonding in diborane is electron deficient bonding, so I right away have a way out if I know something about the bonding in organic compounds to deal with the basic problem for a theoretician, how to form more bonds with the same number of electrons. This use of the Cambridge structural data file, that's very, very chemical. But just the idea of using P equals 1 atmosphere information to make inferences about higher pressure. This about transferring electrons and packing positive and negative charges, that is also a good part of solid state inorganic chemistry. So these are the chemical things that enter into this. So I now want to say something in general about this and why this is fun for me, this high pressure field. There is also another reason, aside from the fact that it's just plain fun to see the structures, and that's a philosophical background. So I'm very interested in why we do things and how we do things in a general reflective way. And one of the things that bothers me about the interaction between chemistry and physics is reductionism. So reductionism goes back to Descartes. Probably this is not blaming the French for everything, but Comte was involved in a general idea that there is a hierarchy of sciences, which, and even outside of science, from humanities to social sciences to biology to chemistry to physics to mathematics, maybe, and with that is defined a depth of explanation so that you understand something by going down this chain, biology in terms of chemistry, chemistry in terms of physics. Philosophically, this is old stuff. No one believes it in philosophy. And empirically, though people buy it for their own advantage, it's not of much use in science either. You just have to look at attitudes of physicists toward mathematics to get some idea. Usually the reductionist chain stops at wherever we are. So I think it's unreal. I think there are, and I could talk much more about this. I think there is levels of understanding, and there is horizontal and vertical understanding. Vertical understanding is reductionist in nature. Horizontal understanding is when understanding something on the level which is the same level that as you are of complexity. It looks quasi-circular, but it's not. Let me give you an example. If someone sends me an anonymous letter in the mail, and in it is a line from a John Donne poem, love is a growing or full constant light, and his first moment, afternoon, is night. Knowing the sequence of firing of neurons in the mind of the person who sent it to me, in my mind as I read it, in the mind of John Donne as he wrote that poem, knowing the sequence of biochemical actions behind those firing of neurons will get you a lot of Nobel Prizes, but has nothing to do in the world with understanding that poem. That poem is understood in the context of the English language and the psychology of the persons involved in this triangle. And though it's the same level, the understanding is on the same level. I believe that most of what is interesting in chemistry, most of the conceptual structures of chemistry are not reducible to physics, or they wilt at their edges when they try to reduce them to physics. I'm thinking of things like substituent effects, acidity, basicity, aromaticity, all the things, stereochemistry, all the things that make chemistry interesting to me. So, okay, so I've gone on about reductionism. In the meeting ground of chemistry and physics, part of what I'm interested in is in reducing the chemist's belief that really understanding is there by the physicists. I can actually give you an argument why I think physicists understand molecules less than chemists. But that's another story. What I'm interested in is in reducing the somehow impoverishing belief in a reductionist chain. Okay, so yet there is a meeting ground. The meeting ground has grown in the last 50 years. It has grown with the high-temperature superconductors, with the fullerenes, with all these fields of intersection on materials, which are just incredible. And I'm interested in that meeting ground. I'm interested that chemists enter that meeting ground without feeling inferior in understanding to physicists. Okay? So this is where the reduction comes in. So now I have one such field is the electronic levels of extended systems, solids and surfaces. And I wrote a book, which based on 2 articles, in which I had 2 aims. One was to, in that meeting ground, you had to use the language of solid-state physics. You had to use the language of bands and not bonds, of densities of states, of Fermi surfaces, of Fermi levels. All that you had to use. And that was not, in general, part of the education of chemists. It stopped at that BCC, FCC in the freshman course, and maybe that metallization argument that I gave you. So in this book, one of the purposes was to make chemists less afraid of the language of physics by teaching them a language with only 2 equations in a whole book. And you can be sure that the solid-state physics course wasn't going to do that. It was going to use Ashcroft and Mermin, and it was going to have lots and lots of equations. So, and I did that, and I had another purpose. I wanted in this book to teach, I wanted to teach physicists that there was something of value once we established a middle ground in the language between bands and bonds, that there was something of value in chemical ways of thinking about this. Okay, so this book has been very successful, and on the first of my purposes, there are 2, 3, 4 generations of chemists who have learned not to be afraid of the solid-state language on the basis of this book, together with a solid-state physics course. On the second aim, to make physicists aware that there's something of value in the chemical ways of thinking? Nada, rien, ni одной копейки, nothing. Okay, so they're a bunch of arrogant bastards. So, okay, now you can see why I'm interested in the high pressure field. All of a sudden, I have another chance. I have a field in which there are physicists and chemists together and engineers, and they're interested in these concepts. And I have a chance of maybe convincing the physicists that there's something of value in the chemical ways of thinking. That's what this lecture was about. And will it work? Well, I doubt it. But I'm having fun. Thank you. Yeah.
Okay, let's see if there are any questions from the audience. Jim?
I had to write out, one equation was to write out the symmetry adapted, essentially the block functions, that the orbital was a sum of e to the ikna times the wave function in each unit cell. And I don't remember the second one.
Question back here. There's a microphone, if you could just hang on.
Do you think that would be of any advantage to study the high pressure chemistry of your molecules, but not by squeezing, but by colliding them? In principle, the free electron lasers are, with femtosecond resolutions, are allowing to study those transient kind of reactions in situ.
Yes, so very much so. So they're now we're talking about the collision of two molecules, maybe done many times over. So it's a single molecule reaction, and you're pushing it just mechanically into a regime of interaction. It's the time of the collision is fairly short, but sometimes you get interesting things. You get orbiting of various kinds of the molecules. Yes, you could learn something from that. Another thing that we have done computationally, which I think could be implemented experimentally. Computationally, we have used a helium compression chamber to study what a molecular reaction. So if I want to see how two benzene molecules interact, I have put them into, in the initial step of formation of one of those nanothreads, the initiation step. So I have put two benzenes together, and I have put around them X helium atoms. And then I've squeezed, I have a box of certain volume. That volume is what's controlling the pressure. And I repeat that box because I have to do translational symmetry. I have to have some. Anyway, I put in enough heliums so as there be some heliums between those two molecules that are reacting, and they're replicas in the next unit cell. The heliums adjust to the position of the molecules. Why am I using helium? Because helium is, at least at moderate pressures, under 500 gigapascals, not reactive with molecules. Put it in electronic terms, the 1s level of helium is 26 eV below ionization. The 2s and 2p is a large distance above. Molecular levels are in between. There is no electron transfer between helium to the molecule or from the molecule to the empty levels of helium, I think. And so the helium is just a pressure medium. It doesn't matter where I put the helium atoms. In the beginning, we took a helium FCC crystal, we cut out a hole, and we stuffed the molecules in there. But later I realized it doesn't matter. The heliums will adjust to the pressure and will just communicate the pressure to the molecule. And then I'm wondering whether this could not be implemented experimentally, actually. It was a theoretical device. But if you could, in some ways, that's what you do in a diamond anvil cell, because often you have helium as a medium.
Another question back here.
In your talk, you focus on the pressure. There's also another degree of freedom, the temperature,
Yes.
which is very interesting too. So in your diagram, you should also have the other dimension, other degree of freedom. Can you tell us a little bit about the situation with respect to temperature and also the quantum effects when you lower the temperature to lower and lower the temperature?
Yes. So the quantum effects may dominate for very low temperatures, as you say, when tunneling becomes important in chemical reactions, but also in general in determining the surface, especially for hydrogen and lithium and other low things. People have observed the influence of tunneling on chemical reactions in the gas phase or liquid, even for carbon. The temperature, I got into trouble one time when I said on temperature that there is no chemistry on the surface of the sun. Well, someone then sent me a spectrum of H2 so the surface of the sun is not well defined. There are flares, there is cooling, and there's all kinds of chemistry going on the outside. And especially in brown dwarfs, there is a lot of organic molecules being produced. The temperature in general will, so at 4,000 degrees, 4,000 K, you can still have hydrogen molecules so that you can detect them spectroscopically. At low temperature, you mentioned tunneling is important. There are pressure and temperature combine in interesting ways, and this is of interest to the astrochemical, astrophysical community. You may have a reaction that's exothermic, but if there is no third body to carry away the energy, it'll just come apart if it's low enough pressure and there aren't enough collisions. There is a lot of interesting photochemistry becomes more important in outer space than it is on Earth. Anyway, high temperature and pressure combine in interesting ways. Some of the most interesting things are phases of matter that are high temperature phases of some inorganic substances, even as the pressure isn't changing much. That there is, it's very hard for us to think about this except in ways of doing molecular dynamics or atomic dynamics. I don't have too much experience with it, but it's a very interesting thing.
Other questions? Ben?
You're well known, and as Tom mentioned, your interest in art and poetry, and as well as the hard sciences. Was that something that was with you all of your life, or did that develop later? And do you think that? Probably that's all I would ask about it.
So, of course, it's in part in us, but I think for me, the world opened up in college at Columbia through a core curriculum which had required courses in humanities and social science, but also courses in history of art and in literature. And whereas the chemistry I did, the chemistry courses, so I started out as a pre-med. It was a natural thing for the only child of Jewish immigrant parents. Just as it is today, I have the same conversation with the son of your local Korean grocer. They are likely to be at Cornell and likely to be a pre-med. Okay? And my job is to counsel them how to tell their parents that they don't want to be a doctor. So chemistry courses were boring. The only thing kept me going in chemistry was summer research experiences. One at National Bureau of Standards then in downtown Washington, now NIST, and another one at Brookhaven, and actually involving a reaction that I mentioned that involved a neutron. So it was carbon-12, proton in, proton neutron out to carbon-11, and we were measuring the cross-section of that. Anyway, while the science courses were not interesting, the world was opening up in the humanities and the arts. And my history at Columbia was that I worked up enough courage to tell my parents I didn't want to be a real doctor, but I didn't have enough courage to tell them I wanted to be an art historian. That would have killed them. And so I kept these interests from college on, in poetry, in Japanese literature, in art in general. And I've been fortunate enough and I kept them. The most difficult time to keep them was around age 30 to 35. And the reason was the science was going too well. And the science was both demanding and addictive. And I was starting a family. And with all those things, there was little time for these interests. But I kept them going. At least I kept reading. Eventually, I started sitting in on courses to keep up my languages. And then eventually I got back to these. Is it that I've had the luxury of being able to do this and that other people cannot? And I tell you, out there in the poetry world, I mean, I keep a logbook. It's a different world. The best chemistry journals, the acceptance rate is 30%. To say you go the step below and it's 85%. And in that same journal in poetry, the acceptance rate in that second-rate journal is 1 or 2%. So it's a different world out there. When I submit a poem, I write a submission letter. These can't be very long, but I write a submission letter on chemistry department stationery. Why do I do this? Because I know the process. The process is the local magazine is put out by the University of Tennessee, and it is staffed by graduate students and Master of Arts in Literature program. Each graduate student, many more people think they write poetry than are willing to write for poetry books. So the submission rate is high. They're not willing to buy poetry books. Submission rate is high. What happens is there's a poor graduate student who's doing this as volunteer work, and they read 50 poems that come over the transom every day of the year. And they pick 2 or 3 to show to the editor. So what I'm hoping, hope against hope, is that graduate student at least glances at the submission letter. They don't. They've learned not to read them because they're boring. But that they glances and sees this is a weird guy from a chemistry department writing. Even now, with having a publication record, my average is about 10% with those journals on the submission. It's a different world, and the chemistry, doesn't matter in that. But I'm not unhappy because it puts me in touch with this creator community in the arts, and it's a very interesting group of people.
Well, I think that's probably a good note to wind up and thank our speaker again. And I think you've found an interesting place in the high pressure regime where the atoms and molecules are fighting really hard to resist the temptation to go over to the dark side and become metals. And in doing so, they distort themselves in interesting ways, which gives rise to this very rich phenomena that really can't exist in either the physics world or the chemistry world. So thank you for telling us about